16 was really a wealth of information. And we had two different types of new integrals. We had line integrals and then we had surface integrals. And with both of those, we saw them in a variety of contexts, and sometimes we had some nifty theorems or tricks for evaluating them, but they didn't always apply, so we needed to know when they did and when they didn't. So what I want to do is in the next two videos, just go through a quick overview of all of the different ways in which we saw, for this video, line integrals in chapter 16, and for the next one, surface integrals. Okay. So, most basic idea of a line integral is that I would have the integral along C of f of p ds. Now, p here is just representing a point. So in R2, p is just the point xy. In R3, p would be the point xyz. Okay. All right, and this little s here stands for arc length. So we're integrating with respect to arc length. Okay. Now, the way we evaluate something like this is we need to parameterize the curve. If we're working with a line integral or a surface integral, that's the key. You've got to parameterize. Because this is a single integral, I need to express everything in terms of one variable. That's going to be my parameter, because that's the beauty of a parameterization. It matches the number of variables to the dimension of the object. A curve is a one-dimensional object, but if it's living in 2-space or 3-space, I'm describing points on that curve using 2 or 3 variables. When I parameterize it, so if I write it as r of t, where t varies from a to b, now I can describe everything in terms of one variable. And so this becomes the integral from a to b of f of r of t. That's just using this function composition to express points on the curve in terms of that one parameter. And then we always have a scaling factor when we switch from integrating with respect to one thing to integrating with respect to something else. And the scaling factor is the magnitude of r prime of t. Okay, so that's just a straightforward line integral if I'm given a real valued function to integrate. The main example that we saw of this was a work integral where I would have a vector field. Okay, so we would have the integral of f dotted with t ds. Now, f dotted with t is a real valued function. So it's just my integrand is this dot product. But I'm building that dot product by using this vector field that I'm given f. Okay. And if I parameterize my curve the same way, that's going to become the integral from a to b of f of r of t dotted with t is just the unit tangent vector. So that's just r prime of t normalized, but then we get our scaling factor, which is the magnitude of r prime of t, and that cancels out. So this work integral is super, super nice because the formula simplifies to the integral of just f of r of t dotted with r prime of t dt. And that scaling factor, since it's a magnitude, it's a square root of the partial derivatives, or it's the square root of the component derivatives squared. That sometimes makes the integral a little bit complicated. Really nice to see it canceling out when we're doing a work integral. Now I'm referring to this as a work integral. That's what this represents if f is a force field. Of course, we did see that if f is a velocity field, this actually represents something called circulation. Okay. So there's our basic line integral. And there's the main example of a line integral that we have, which would be this work integral. Okay. Now, we saw for work integrals some special cases. So, if f is conservative, So if f is the gradient of some potential function, then I can say the integral along C of f dotted with t ds, I can evaluate it the way I normally would, but in this case, this is going to be independent of path. And if I parameterized C as r of t, where t varies from A to B, so that my curve here went from r of A to r of B, I can actually evaluate this as just f of r of B minus f of r of A. It's the potential function evaluated at my ending point minus the potential function evaluated at my starting point. Okay. And that's the fundamental theorem of line integrals. Theorem. And that just says that work integrals for conservative vector fields are independent of path. Okay. A nice result of that is, again, if f is conservative and if C is closed, so remember, if it's closed, that just means it loops back on itself. Okay. Then the integral of f dotted with t ds is just going to be 0. Now, both of these things, it being independent of path and it automatically being 0 if I'm on a closed curve, only apply if my vector field is conservative. Okay. So, if you don't have a conservative vector field, you've just got to evaluate the work integral. If you do have a conservative vector field, sometimes one of these can be a shortcut. Certainly if you've got a closed curve, this is a definite shortcut. Sometimes finding a potential function and evaluating it can take longer than actually just evaluating the integral. Okay? But sometimes that's easier than evaluating the integral. And the other way that you could use this is, let's suppose that I have a path that's going from A to B, and it's a very convoluted path, so it would be difficult to evaluate, but I know that my vector field is conservative, so that this is independent of path. I could just draw a straight line path from my starting point to my ending point, and I could use that path instead. Okay. So that's a very nice thing that applies if I have a conservative vector field. Okay. All right, in the context of this, I'm going to just remind us of the different types of notation that I can have for a work integral. Okay. Now this notation applies whether my vector field is conservative or not, but it also applies just to work integrals, not to line integrals in general. Okay. So if I have the integral along C of f dotted with t ds, we can write that as the integral along C of f dotted with dr as well. Okay. We can also, if f is pq. Now I'm just going to write this out as if we're in 2 space. Obviously, if we were in 3 space, there would just be a third component function, which I would probably call r, because that's the next letter in the alphabet. Okay. But if that's the case, I could say that the integral along C of f dotted with t ds is the integral along C of p dx plus q dy. Okay. Now, in the case that f is conservative, this actually represents the total differential of the potential function. But you can see this even if f is not conservative. I'm not a huge fan of this notation, but it certainly does work. And just a reminder, the way you would evaluate something like this, usually what I do is I actually just translate it back to this notation because I find this more user-friendly. But if you prefer, you could evaluate this if C is r of t, where t varies from a to b, you could say this is the integral from a to b of p evaluated at r of t, because p would be a function of x, y, so now I'd be evaluating it at this, times x prime of t dt. That's the scaling factor I get in switching from dx to dt, plus the integral from a to b of q of r of t times y prime of t dt. So if you've got an integral and it's a line integral, but you're integrating dx or dy, your scaling factor for switching to dt is just the appropriate derivative, the derivative of x as a function of t or the derivative of y as a function of t. Okay, excellent. So we also have a couple of theorems, Stokes's theorem and Green's theorem, that apply if C is the boundary of some surface. Okay. So if we're in 3 space and C is the boundary of some surface S oriented positively with respect to S. Remember, what that means is that S, our surface, is going to have some orientation. For our curve to be oriented positively with respect to it, we basically use the right-hand rule. If I take my right hand and I curl my fingers in the direction that C is oriented, my thumb should point in the direction of the principal normal vector to the surface S. Got to do that with my right hand. It's called the right-hand rule. Okay, if I have that, then I can use Stokes's theorem. And Stokes's theorem just says that the integral along C of f dotted with t ds is the double integral along S of curl of f dotted with n ds. So I can switch from this line integral to a surface integral instead. Okay. Now, that's particularly useful if C happens to be piecewise smooth. So, for example, if C was the boundary of a triangular region, well, it's going to have 3 different boundaries. That would be 3 line integrals I'd have to do, or I could just integrate over that triangular region. Okay. So that can be fairly useful if I have that. Notice Stokes's theorem only applies, however, if C is the boundary of S, which means it's going to have to be a closed curve. If I have a curve like so, that's open, well, that's not closed. I don't think we call it open if it's not closed. Sorry. Okay. If I have a curve that is not closed, so that the starting point and the ending point are different, there's no way it can be the boundary of anything. Stokes's theorem does not apply. And in 2 space, Green's theorem, which is the analog of this, wouldn't apply either. So let's go ahead and state what Green's theorem is. Okay. So in R2, if C is the boundary of a region D oriented counterclockwise, and if F is equal to PQ. Okay. Then we can use Green's theorem, which states that the integral around C of f dotted with t ds is just the double integral over d of, it's the partial of q with respect to x minus the partial of p with respect to y dA. Okay. And you know me, I'm horrible at memorizing formulas, particularly if they involve subtraction problems. I can remember that because that's essentially what I get if I just take the determinant of this symbolic matrix. I put the, I put the operators for the partial derivatives with respect to x and y in the first row, the component functions p and q here, and then I get the partial of q with respect to x minus the partial of p with respect to y. All right, so Green's theorem and Stokes' theorem give me a nice alternative if my curve is the boundary of a surface. Do not use them if the curve is not the boundary of a surface. If you don't have a closed curve, it doesn't enclose some surface, and then you just have to evaluate the line.